This week, we will work on constructing proofs in predicate logic. This is really the continuation of constructing proofs in propositional logic. There is no difference, except we will introduce some additional rules of inference in predicate logic. Okay? So everything remains the same as propositional logic, except that we will introduce a few additional rules of inference that is special to predicate logic. Okay? So let's move on to additional rules for predicate logic right away. The first additional rule for predicate logic is called quantifier negation, QN in short. The rule says when a negation sign is moved across a quantifier, universal quantifier is switched to existential quantifier and vice versa. Okay? So for example, we have a negation sign in front of a universal quantifier statement, and when you move this negation sign behind universal quantifier, you can do that, but you have to change the universal quantifier into existential quantifier, like this. Okay? And same thing happens when you move negation sign to the front. This existential quantifier should be switched to universal quantifier. So that's the rule, okay, called quantifier negation. Let us see an application of this quantifier negation. For example, suppose you have this universal quantifier statement at the beginning. You can derive this statement from this by using. Remember, we have to appeal to all the rules of propositional logic. Okay? And double negation rule allows us to do that. Okay? Whenever you have an expression, you can derive double negation of that. Okay? Now, suppose you want to move one negation sign to the front. Okay? Suppose you want to move one negation sign to the front. Okay? You can do that, but when you do that, you have to change, okay, this universal quantifier into existential quantifier. Okay, so this is by quantifier negation. Of course, you can move this negation sign to the front as well. Okay, so when you move this sign to the front, yes, you can do that. So there will be two negation signs, but this existential quantifier should be switched to universal quantifier. Okay? Okay, like that. Okay? So this is quantifier 2. Okay? Quantifier negation rule. Okay? The next rule of inference for the predicate logic is called universal instantiation, UI in short. Suppose you have a universal quantifier statement to start with. From this, the rule says you can derive a statement which is replaced by A in all occurrences of variable X. Okay? This sentence is obtained by replacing A for all occurrences of X in the original sentence. Okay? So for example, what? To give you an example, suppose you have X, 4X, Fx, then Gx. Okay? Universal instantiation rule says I can derive a sentence obtained by replacing X with a particular name. So, I mean, you can use any letter whatsoever. I mean, I happen to use A, but you can use a different name. Let's say B. Okay, so you can derive FB then GB. Okay, by the rule UI. Okay, that's what the rule says we can do. So A is any name of a particular individual. Okay, so A, B, C doesn't matter. Okay, you pick up a particular name and replace variable with that name. Okay. So intuitively, the rule corresponds to this inference. Suppose this is true. Everybody is tall. Then, of course, it is true that Socrates is tall. Okay? If everybody is tall, then any single individual is tall as well. So this inference is basically what UI is. Okay? The next rule of inference is called existential instantiation, EI. You have existential quantifier statement, and again you can replace X with any name, A, B, C, and draw this conclusion. Okay? Now, unlike UI, however, there is a restriction for EI. Okay? The very important restriction here. This is the restriction. Okay? Says the name A that you will replace the variable with must not have occurred before in the proof or the conclusion. Okay? That's the restriction for EI. Okay? You have to avoid using such names. That is, you have to avoid using names that have occurred in the proof. Okay? Why is that? Why there is such a restriction? Well, the existential statement says that there is at most that there is at least one thing that is such and such. It does not specify which one that is. So you should not use a name that occurred in the proof before. Okay? Because if you use a name that has occurred in the proof, then you are putting in more content than is given by this sentence. Okay. So keep in mind this restriction. Okay. Let's see an inference that violates this restriction. Okay. Okay, so here is a proof. There is one premise, and there is the conclusion. Okay, so the problem is we have to construct a proof for this argument. And in this case, okay, this particular proof commits the error. And we have to identify the error. Okay, so let's see. The second step is obtained from number one by using the rule UI. Okay, so you have applied UI rule for this quantifier, and you use the letter A. Okay, so A replaces every occurrences of X. So this is what you get. Okay. So the second step is fine. Okay, it's there is no restriction about using about the choice of names for UI. But look at the third step. Third step applies EI, okay, existential instantiation for quantifier EY. So replaces the variable y with a particular name A, okay? And the error occurs here. Well, you are not supposed to use a name A here when you do EI. Why? Well, because A occurs before in step 2, right? A is a name that has already occurred in the previous steps. So you should not use the name A in step 3. That if you do that, you violate the restriction that I mentioned, okay, about EI. Okay? So the identified error here is that the step 3 uses the rule EI with a name which has occurred in the previous step 2. So it violates the restriction. Okay, that's the error. So EI is a rule that we need to be careful in using it. Okay. The third rule is existential generalization, e.g. What you start with a sentence that has a particular name occurring in it, and from that you can derive existential statement. There is at least one X such that X is such and such. Okay. For example, suppose you have this premise. Okay, Socrates is a philosopher. If Socrates is a philosopher, then of course it follows that there is at least one person who is a philosopher, obviously. Okay, and that's what EZ says. Okay, we can infer this. Okay. Finally, we have the rule UZ. Okay, UZ says if you have a sentence with a particular name occurring in it, then you can derive a universal quantifier statement. That is, you can generalize to a universal statement. But we have a restriction here too. Okay, the same thing with the EI. Okay, UG has a restriction. The following restriction: UG can be used only when A was initially introduced by UI. Okay, or in the assumption of a conditioner or reduction proof. So for example, if A was initially introduced by, let's say, EI, then you cannot do UG here. Okay? That's what this restriction says. Okay? So we have restrictions for EI and UG. Okay? So those two rules we have to be careful with. Okay? There are restrictions for using these rules in an appropriate way. So keeping those things in mind, okay? Let us look at a particular example. Okay, so next page, proofs in predicate logic. So let's do a particular example here. When we construct proofs in predicate logic, of course we have to use all the rules of the propositional logic as well as the additional rules that we have talked about today. Okay. So let's do a particular exercise problem. Okay. There are two premises, and the conclusion is this. So the problem is we need to derive this from this the premise using all the rules that have been introduced so far. So step 3. I like to do UI of number 2. I can do UI of number 1, but because I have in mind that there are certain restrictions for using EI, I want to do EI first. Okay. So I will do EI of number 2 and get P A and not R A. Okay. That's from number 2 EI. Okay. Number 4. Now I will do UI of number 1. The order in which I do EI and UI is important. Okay. If I do UI first, then I cannot do EI, or I have to use different letter. Okay. The order in which I do EI and UI is important. Okay. So I will do UI of number 1 now. Okay. So by using the same name, A. Okay? I'm allowed to do that. Okay. UI does not have any restriction on what name I can use to replace the variable. Okay. So I will replace the variable X with the same name A. I can do that, right? PA, then, okay, QA or RA. This is from number 1 UI. Okay. All right. After that, I want to do simplification of number 3 and derive PA. Simplification rule, remember, was one of the rules for propositional logic, and which says that whenever I have two things combined by and sign, I can derive either one of them. Okay? Remember, that was the rule simplification. Okay? So I'm going to appeal to this rule to derive PA from this. Simplification number 3. Okay. Now look at 4 and 5. There is a rule I think I can apply to this pair. Do you see that? I can derive this one, QA or RA, from 4, 5 by using the rule MP. Okay, so 4, 5, MP, modus ponens. Okay. After that, I want to derive this one by using the rule simplification again. So 7, I will derive not RA this is by simplification again of number 3. Now from 6 and 7, I can derive what? If you look at the sentence 6, it says something or another. And at step 7, I have the negation of one of them. And remember the rule, disjunctive syllogism says that when I have a situation like this, I can derive QA. QA, okay? This is from 6, 7, DS. 6, 7, DS. Okay, 6, 7 DS. All right, we are almost done. I think I can now derive this one. That was the conclusion. And what I have got so far is QA. Is there any rule that I can appeal to here, rely on here to derive, to get from here to there? There is such rule, right? It's called EG, okay, existential generalization. So at step 9, I say, well, I write down this. There is X, Q, X. And this is from number 8 by using the rule EG. Okay, since I have obtained the conclusion, I have finished the proof. There are many other exercise problems in the textbook, and again, there is no other way to master the techniques of constructing proofs other than doing many problems, as many problems as possible. Okay, so keep working on the problems in the textbook. Okay.